The familiar fade expiration dates in our lives. We've all seen it. The dates stamped on our milk cartons, our medications, even our cosmetics. These dates are more than just numbers. They are indicators of safety and quality. These expiration dates tell us when something is past its prime. It's a simple concept. Over time, things change. Milk spoils, pills lose their potency, and makeup products degrade. That lipstick just doesn't look the same. But what about poisons? Have you ever wondered if they too have an expiration date? It's not like we check the expiration date on a bottle of arsenic. The idea that something designed to be harmful could also be subject to the passage of time might seem strange, yet even poisons are not immune to the effects of time. The idea that something so dangerous could lose its potency is both fascinating and unsettling. After all, poisons are dangerous by design. They disrupt biological processes, wreaking havoc on living systems. But time changes everything. Even these agents of chaos are subject to the same forces of nature that govern the rest of the universe. They degrade, they transform, they lose their edge. Just as the stars themselves are born, live, and die, so too do poisons undergo transformations over time. Their potency can wane, their effectiveness can diminish. The universe is in a constant state of flux, and nothing is permanent. This includes the very substances we consider to be eternally dangerous. Poisons, like everything else, are subject to the laws of chemistry and physics. Their chemical structures can shift, rendering them less effective or even harmless over time. The study of poisons and their relationship with time is a journey into the fascinating and sometimes unsettling world of chemistry and biology. It's a field that forces us to confront the fact that even in the realm of the dangerous and deadly, nothing lasts forever. Everything has an expiration date. This journey into the world of poisons and their expiration dates is not just academic, it has real-world implications for safety and health. It's a journey that forces us to confront the fact that even in the realm of the dangerous and deadly, nothing lasts forever. Everything, even poisons, has an expiration date. Poison, a universe of harm. What exactly is a poison? The answer is surprisingly broad. A poison is any substance that can cause harm to a living organism. This harm can range from mild irritation to severe illness, even death. Poisons don't discriminate. They can be natural or artificial, fast-acting or slow-burning. Consider cyanide, a fast-acting poison that disrupts the body's ability to use oxygen. Then there's asbestos, a naturally occurring mineral whose fibers, when inhaled, can lead to lung cancer decades later. From the arsenic in groundwater to the venom of a deadly snake, poisons are all around us. Some poisons are accidental byproducts of human activity, while others are carefully engineered for specific purposes, like pesticides or certain medications. The sheer diversity of poisons makes it difficult to make sweeping statements about their behavior over time. To understand how poisons age, we need to delve into the world of chemistry and explore the differences between organic and inorganic toxins. Nature's arsenal poisons from the earth. These poisons are as diverse as the ecosystems they inhabit, each with its own unique story and purpose. Poisons are not just the stuff of laboratory concoctions and industrial accidents. They are deeply embedded in the natural world around us. Nature itself is a master chemist, having produced a vast array of toxins over millions of years of evolution. These toxins can be found in the most unexpected places, from the petals of a flower to the silk of a spider's web. These natural poisons, often found in plants and animals, serve a variety of purposes. They can be used for defense, predation, or even competition among species. Plants, for example, may produce toxins to deter herbivores from eating them. These chemical defenses can be incredibly effective, ensuring the plant's survival. Animals like snakes, spiders, and scorpions use venom to subdue prey or defend themselves against predators. These venoms are often highly specialized, targeting specific physiological systems in their victims. These natural poisons are often complex mixtures of chemicals, each component playing a role in the toxin's overall effect. Scientists study these mixtures to understand their mechanisms and potential applications. Consider the deadly poison of the pufferfish, a delicacy in some cultures. Despite its danger, it is highly prized for its unique flavor and texture. The poison, tetrodotoxin, is concentrated in the fish's liver, ovaries, and skin. This potent neurotoxin can cause severe symptoms and even death if not prepared correctly. It's a neurotoxin, meaning it disrupts the nervous system, causing paralysis and, in sufficient doses, death. Understanding how these toxins work can lead to medical advancements and new treatments. The existence of such potent toxins in nature is a testament to the power of natural selection. Over time, organisms have honed these chemical weapons to perfection. It's a reminder that in the constant struggle for survival, organisms have evolved a dazzling array of weapons and defenses, many of them chemical in nature. These adaptations highlight the intricate and often perilous balance of life on Earth. Section 4. Organic toxins, decay and diminishing danger. Organic toxins, like those found in plants and animals, are composed of complex molecules containing carbon. These molecules are susceptible to degradation over time. Factors like temperature, humidity, and exposure to light can cause these molecules to break down, rendering the toxin less potent. Think of a banana. Fresh, it's a tasty treat. Leave it on the counter for a week and it's a mushy mess. The same principle applies to many organic toxins. The complex molecules that give them their potency break down, losing their structure and therefore their ability to interact with biological systems. This degradation process is often accelerated by enzymes, proteins that act as catalysts to speed up chemical reactions. In nature, enzymes play a crucial role in breaking down organic matter, including toxins. This decomposition is essential for recycling nutrients and preventing the buildup of harmful substances in the environment. So, while the venom of a freshly deceased snake might still be deadly, over time, the organic molecules in the venom will degrade, rendering it less toxic. Section 5. Inorganic toxins, a different kind of time. Unlike their organic counterparts, inorganic toxins are not composed of carbon-based molecules. These toxins, which include heavy metals like lead and mercury, as well as arsenic, don't degrade in the same way that organic toxins do. Instead of breaking down into harmless substances, inorganic toxins tend to persist in the environment. They may change their chemical form, but their fundamental toxicity often remains. For example, mercury can exist in different forms, such as elemental mercury, inorganic mercury compounds, and organic mercury compounds. Each form has different toxicological properties and can have varying effects on human health. However, all forms of mercury are considered toxic and can accumulate in the body over time, leading to a variety of health problems. The persistence of inorganic toxins makes them particularly problematic from an environmental perspective. They can accumulate in soil, water, and the food chain, posing a long-term threat to human and animal health. Section 6. When time brews a stronger poison. While many poisons lose their potency over time, some actually become more dangerous. This counterintuitive phenomenon can be quite alarming. This can occur when the poison undergoes chemical reactions that transform it into a more toxic form. These transformations can be triggered by various environmental factors. One striking example of this phenomenon is seen with the botulinum toxin, one of the most potent toxins known to science. Its potency is a testament to the complex interplay of biological and chemical processes. Produced by the bacterium Clostridium botulinum, this toxin is responsible for botulism, a rare but serious illness that attacks the nervous system. The severity of botulism highlights the importance of understanding how toxins evolve over time. Interestingly, the botulinum toxin itself is not inherently toxic. It exists initially as a precursor molecule. It's a precursor molecule, meaning it needs to be activated before it can wreak havoc. This activation is a crucial step in the toxin's life cycle. This activation occurs through a process called proteolysis, where enzymes cleave the precursor molecule, transforming it into the active toxin. Proteolysis is a common mechanism in many biological systems. In the case of botulinum toxin, this activation process can actually be accelerated under certain conditions, such as exposure to certain types of bacteria. These bacteria can act as catalysts, speeding up the transformation. This means that, over time, the potency of botulinum toxin can actually increase if the conditions are right. Factors like temperature, pH levels, and the presence of other microorganisms can influence this process. It's a stark reminder that the relationship between time and toxicity is not always straightforward. Understanding these dynamics is crucial for developing effective countermeasures and treatments. Section 7. The complex legacy of